All right, what's up everybody? Welcome back to Rob's Office Hours. Today we're talking about the geometry of solutions to systems of linear equations, okay? So what does this really look like? I'm going to start with some basic examples of giving you two linear equations and two unknowns, okay? And what does the geometry of these things look like? Well, so you want to think about these things as being paired. Now remember, solutions to systems of equations are an assignment of variables which satisfy all of the equations involved in the system. Okay, so what I can think of here is I can think of these as lines. All right, so if you want, you can think of these alternatively as what? Y equals x minus 2, and this one is y equals 6 minus x, right? Just solving for y, and then I could graph those. All right, so if I graph those, what do those look like? Well, I'm going to try and do my best, but we'll see. Okay, so y equals x minus 2, so that says go down minus 2, and go up. Okay, so minus 2, go up 1 over 1, so it's going to look something like this, roughly. Okay, so that's y equals x minus 2. And then this one says, okay, go up to 6, 1, 2, 3, 4, 5, 6. And then go down 1 over 1, so that's 2, 3, 4, 5, 6. So that's going to be something like that, maybe. And maybe I pulled this off, I don't know. This is y equals 6 minus x. Okay, now how do I solve this? Well, method of elimination says that, look, if I add these two equations, what do I get? I would get 2x plus 0y equals 8. So that would tell me x equals 4. And if x equals 4 and I plug that back in here, this would say 4 plus y equals 6. So y equals 2. And if I look at that as a point, 4 comma 2, it's saying that's my unique solution. And miraculously, I actually did pull this off. The intersection is at 4 comma 2, okay? I'm actually kind of impressed with that, I'm not gonna lie, because that was not planned. Okay, so anyway, so that unique intersection point, what I notice is that I have a unique intersection point of 4 comma 2, okay? So we would say the language would be that this system has a unique solution, okay? So I have a unique solution. Okay, so that's a solution type for systems of equations, is I have a unique solution, one and only one intersection point for all the equations, okay? Now, what would I get over here? Well, this one looks like what? If I want to graph these, this looks like something like y equals what? X minus 3, okay? And then what happens here? So if I move the 2x and I divide by 2, I would get y equals 2x over 2 is just x, and negative 6 over 2 is minus 3. Well, it's the same line, okay? They look very different, but it's the same line. Okay, so if I graph this, it kind of looks a little silly to graph, but it's like 1, 2, 3, 1, 2, 3. So it's going to do something like this, okay? So this is just y equals x minus 3. And what I notice is that because these are the same line, they intersect at every single point, right? You give me an x value, it will satisfy, and I can solve for the y value. You give me x is equal to, say, 10, right? If x is 10, then y is 7, then that would give me a solution here. Okay, so x was 10, y was 7, so this is saying 14 minus 20 is negative 6. Hooray, they're the same. Well, of course they're the same. They're giving you the same line. So what this says is that every point on this line is a solution to the system of equations. So in particular, we have infinitely many solutions. Okay? So we just discovered a second type for systems of linear equations. We have a unique solution and we have infinitely many solutions. Okay? Now this one's going to illustrate the third type, and what's nice about linear equations is that there's only 3 types of solutions. Okay? There's a unique solution, there's infinitely many, and then let's figure out what's going to happen over here. Okay, so if I try and graph this, this will be y equals what? 5 minus x. Okay? And this will be y equals, okay, what's going to happen? I'm going to get 10 thirds. Okay, if I move 3x over, subtract 3x, divide by 3, I get minus x. Okay? So what I notice is, look, these lines are parallel because their slopes are the same. The slope is -1, but they have different coordinates for their y-intercepts. Okay, so if I look at this, that's concerning. This one's saying I go up to 1, 2, 3, 4, 5. I go up to 5, and I go over 1, 2, 3, 4, 5. I go down there. Okay, so this is the y equals 5 minus x. But this one is saying go up to 10 thirds. Let's see, 3 goes into 10, 3 and change. So that goes up to 1, 2, 3 and change. And that's going to go over out to 3 and change. So it'll be something like this. I'm trying my best. All right, that's all I can do. And this one is y equals 10 thirds minus x. So what I notice is that these are parallel. And the key is that they never intersect. Well, over here, let's come back to this one. Intersection points correspond to solutions to the system. Intersection points, even if there's infinitely many, correspond to solutions to the system. So if you never intersect, then there are no solutions. Okay? So those are no solutions. Sometimes people call that system of linear equations what's called inconsistent, meaning that it doesn't have solutions. Whereas things that do have solutions, you call them consistent. All right, so that's just some language associated with that. But that gives you the geometry of solution types for systems of equations. And what's beautiful is that this isn't special to 2 equations and 2 unknowns. This could be 50 equations in 7,000 unknowns, things like that. There are only 3 possible solution types for any given system of linear equations, and they are either a unique solution, infinitely many solutions, or no solutions. Okay? Now, depending on the number of variables and the number of equations, you might be able to eliminate one of these solution types and things like that. But as just kind of a broad universal thing, you would say that linear systems, they have 3 possible solution types, either no solutions, infinitely many, or a unique one. All right? So there you go. There's the geometry of solution types to systems of linear equations. As always, like, subscribe, comment down below. These are my office hours, so please ask me questions, and we'll keep on moving.